going to go over the methods for balancing oxidation-reduction reactions in an aqueous environment. This is only for an aqueous environment. If this is taking place in some other environment, then this will not apply. And here is a sample oxidation-reduction reaction. Permanganate reacting with iron to give iron ions aqueous and manganese ions aqueous. Now, if I was asked to balance this, it would be very difficult. I would have to first balance the oxygen, and I could add water to the other side to get oxygen, and then I can add hydrogen to the other side. And after that, I would think that it would be balanced if I did that. However, I would be mistaken, because let me assume for a second that there is no oxygen here, and this is just manganese. If this was just manganese and iron, and then it gave me iron ions and manganese ions, on the surface it would appear to be balanced, but it would not be, because there are different charges. Here manganese has +7, oxygen is -2, so this would be a +7 manganese. And supposing that these oxygens were gone, and this was +7, this was +2. So let me make these oxygens just disappear for a second. This is just hypothetical. Would this reaction be balanced? And on the surface it does look balanced because there's one manganese, one iron, but the truth is they're not balanced because there are missing electrons. Here the charges would total up to be +9, and here they would total up to be +7. So that means electrons are appearing out of nowhere, which doesn't happen. So in order for this to be a balanced reaction, the electrons need to be balanced. And that is the main difference between balancing a regular equation in the past, a regular stoichiometry equation, and balancing a oxidation-reduction reaction. So let me undo all this so I can get back. There we go. So if it's about balancing more than just the elements, it's about balancing electrons as well, then how do I go about doing that? And that's where I follow this method. First, I'm going to write separate equations for the oxidation portion and the reduction portion. Then for each portion, I'm going to balance the elements except for hydrogen and oxygen. And this will be very easy to understand when I go through and actually do it for this reaction. But I'm just going to give a brief overview. So after I balance the elements except for hydrogen and oxygen, and this will become apparent why, because I'm then going to balance oxygen by adding water, H2O. After I add water, I'm then going to balance the hydrogens by adding H+. Then I'm going to balance the charges by using electrons. And the reason I can add water and H+ quite freely is because this is taking place in an aqueous environment, like water. And there's plenty of water available in water, and there's plenty of H+. And the reason for that is for a reason I can't really go into because I would have to learn about chemical equilibriums and more about acids and bases, which I will learn later on in general chemistry. This is one of those things where I would definitely have preferred that this be taught after atomic theory and acid and chemical equilibriums, because it's very important. It's not critical, I guess, for understanding the general concept that electrons are being transferred. That's all that's really trying to be given, or I guess that's really the main point of learning oxidation-reduction reactions right now. It's just the idea that electrons are being transferred. But it's useful to know about equilibriums and what is happening, because the environment is very important that is taking place in for this particular reaction. So I balance those out, then I balance the electrons, then I equalize the number of electrons transferred, and what I mean by that will become apparent when I do both of these steps. Then I add both of these reactions, these separate reactions. I would have done this for both of the separate reactions. I would have done the reduction part and then the oxidation part. Done those separately, then I add them back together. And then if it's a base, this is an acid, but if it was a base, I would cancel out the H pluses with OHs, and then I would cancel out identical species. So anyways, now that I've quickly gone over it, let me begin. first I want to break this reaction apart into two pieces, the oxidation part and the reduction part. And it's not really important which is which. What is important is that they simply be broken apart. Here it's very obvious which is the oxidation and which is the reduction. Sometimes it's a little bit trickier because it won't be obvious because they won't have plus charges. They might be bonded to something else, in which case I would have to tally up I would have to set oxidation states. So here I can see that manganese is +7, oxygen is -2, iron here is +2, iron here is now +3, and manganese is now +2. So here manganese has gone from +7 down to -2. So it has been reduced. So this is the reduction portion. So I'm going to write this out separately. MnO4 minus Mn2 plus. This is the reduction portion. It's not really important which is which. It's just important that they be separated from each other. And now here's the oxidation. Iron 2 plus iron 3 plus. This is oxidation, reduction. So let me go back up to my chart. I mean, I already know how to do this, but just so I can show myself step by step. So I've written them out in separate equations, so that's done. Written out in separate equations. Now for each step, balance all elements except for hydrogen and oxygen. So I'm going to do that first. Balance the elements except for hydrogen and oxygen. There's one manganese, one manganese. So this is already balanced, one iron, one iron. This is already balanced. That might not always be the case. I might have had Mn2O4 or something. That's not a real thing, but if it was, then I'd have to balance it out by adding 2 to the other side. But they are already balanced. So that's check. Balance oxygen using H2O. Now I can do these both at the same time, or I can just do one and then do the other. I'll just do one and then the other. Or actually, it doesn't really matter. It's whatever I prefer doing. I might want to do them both simultaneously, or I might find that I confuse myself, and I might want to do one reaction and then do the other one. I think I'll just do one at a time for now. So I'm going to balance the oxygens using water. Here there are 4 oxygens. I'm going to need 4 oxygens on this other side then. So I'm going to add 4 waters to the other side. It's a liquid. So now that I've done that, I've balanced oxygen using H2O, I need to balance hydrogen using H+. So this side has hydrogens on it now because I've added 4 waters to it. Now this side needs to be balanced out by adding H pluses to this side. Here I have 4 H2O, which means there are 8 hydrogens on this side, so I'm going to add 8 H plus over to the left side. Now that I've done that, I balance the charges using electrons. And what do I mean by that? Well, this side has a plus for the hydrogens and a minus for this ion. This side has a 2 plus for manganese, and then this side is equal because hydrogen has an oxidation state of +1 and oxygen has a oxidation state of -2, and there are 2, so these are going to be equal to 0. But I have 8 hydrogens, so there's going to be 8 plus 8 over here, and I have 1 manganese. So this is going to be this side of the equation. If I divide this equation in 2, this side of the equation is going to have +7 total charge, and this side is going to have +2 only. So in order to balance that out, I'm going to add 5 electrons to the left side. And electrons are a negative charge of 1. So that will, if I add 5 electrons, this is going to bring this down to -2, or +2 I mean, and then they'll be equal. So I have 5 electrons, and this is a symbol for an electron, an E with a minus sign over it. And then I just rewrite everything else out. Now, it's critical not to accidentally forget something. Sometimes you can have so much stuff in these oxidation-reduction reactions, it can be easy just to forget to add hydrogens or waters or something. So yeah, I got hydrogens, permanganate, manganese ions, water, got them all, then I got the electrons I added. So I go back up here and I've done all of this for my one side of the equation. Now I need to do this for the other side of the equation over here, this iron to iron 2 plus to iron 3 plus. Fortunately, this one is going to be quite a simple one. So let me just sort of circle this so I know that this is not my final answer, but that I know that this is my half. I'll just make a note. This was the reduction part. Because sometimes these equations, these oxidation-reduction reactions can be a bit messy. Alright, so now let me go on to, goes from 2 plus 3 plus. Yeah. So now I do this step number 2 all over again for the other part, the oxidation part. Balance all elements except for hydrogen and oxygen. I have 1 iron on this side, 1 iron on this side, so that's already balanced. So that's fine. So there we go. Double X or double line or whatever. Balance oxygen using H2O. There are no oxygens to balance, so this is done. Balance hydrogen using H+. There are no hydrogens, so that's done. Balance the charge using electrons. Now that is something I need to do. This goes from a +2 to a +3. So in order for this to be equal, I should add 1 electron to this side, and then this will be a +2, and then this will be a +2. So let me write this just over here. So now that last step is complete. Now I'm moving on to step 3, equalize the number of electrons transferred. And again, it really goes back to, this step really goes back to the conservation of mass. If I have 5 electrons transferred on this side, I better have 5 electrons transferred over to the other side. There better not be electrons just appearing or disappearing out of thin air. So in order to make this balanced, I could divide by 5, but then I'd have non-integer molecules, and then that's going to be a problem. So I never do that. What I usually do is multiply both sides to a common integer. So here it would be easier for me to multiply this whole equation. I guess I'll circle this, even though this was a very simple one. Sometimes both of them will be quite long like this, but it just so happens this one's not. So in order to make this an equal electron transfer, 5 electrons here, 5 electrons on the other side, I'm going to multiply this entire equation by 5. And both sides are multiplied by 5, otherwise it wouldn't be even. It's just like an algebra problem, really. And I just made a stupid mistake. So now the electron transfer is balanced. 5 electrons over here, 5 electrons on the other side. Now, I add both reactions together. So I've taken them apart, now I'm going to put them back together. So I've done that now. I've added both of these equations back together after I've separated them. And notice that the electrons are on opposite sides. If I balance these two oxidation and reduction reactions, and I find that both electrons are on the same side, I've done something wrong. So that's a good indication. It's a good place to stop and have a second look at what exactly it is I have written out. Because these problems, this is actually a more simple one. They can be very long and tedious, and it's easy to make a mistake. So here's a good place to check and see that electrons, 5 electrons are on one side, 5 electrons on the other side. And that's a good, if there are not an even amount of electrons or they're on both on the same side, then something has gone wrong. So that's a place that I usually definitely check. So now that I've done step 3 and 4, if a base cancel out H plus with the OH, this is taking place in an acid. But what I mean by canceling out H plus with OH would mean that I would add 8 OHs to this left side to get rid of the H pluses, because they wouldn't be existing if it was in a basic solution. So if I add 8 OHs to both sides, I end up with 8 OH minus on this side, and then these H pluses and OHs are going to combine and give me 8 waters. So that is what would happen if it was a base. It would just turn these 8 H pluses into water, and then there would be 8 OH on this side. And then the final step, when I cancel species, I would cancel out these 4 waters, and I would have 4 left on this side, because I would have had 8 H2O on this side. Yeah. So this does not apply, but I just explained what would happen if it did. And now cancel identical species. So here the 5 electrons cancel. If there was water on both sides, I would cancel out. Again, if this had been in a base and I had added OH to both sides, I would have had 8 H2O over here and then 8 OH on this side. However, I would have had 4 H2O on this side as well. So I would have canceled the 4 H2O. I would have canceled 4 H2O on this side, which would have left me 4 H2O over here, no H2O over here, but 8 OH minus. But again, this did not happen because this is in an acid, and there's nothing else to cancel. So my final equation is 8H plus Fe2 plus MnO4 minus wow, I just made a mistake. I forgot to put the 5 out here. See, it's very easy just to drop something and have it be completely wrong because of that. And this is the final answer. Now again, because these problems are long and tedious, it's highly recommended to check that everything balances out, to check and see if I didn't make a mistake, really. And the best way to do that is to look and see if there's a balanced amount of elements on both sides. See here I count up my hydrogens, there are 8. On this side there are 8 over here, 4 times H2, that's 8 hydrogens. I have 5 irons, 1 manganese, 1 manganese, 4 oxygens, 4 H2O, 4 oxygens. But that is not quite enough, because in oxidation-reduction reactions there is a transfer of electrons. So I need to make sure that the charges of both sides are equal. So here I have 8H plus, which is 1. 8 times plus 1. I have 5 Fe2 plus. I have 1 minus. And then on the other side I have 5 3 pluses and a 1 2 plus. And then water is neutral, it does not have charge. So if I add all these charges up together, they should be equal. I have 5 times 2 is 10 plus 8, 18 minus 1 is plus 17. On this side I have 5 times 3, 15 plus 2, that's plus 17. So they balance. So this is a balanced equation. I've checked myself, I checked the elements, I checked the charges, they all come out to be okay, so that means I did this correctly.